Everybody, it's Dr. Morgan. I'm just going to record a really short video today that makes a point that I might make in some of my other videos about the Big Bang, but cannot be stressed too much, which is there is a confusing way in which we use the word Big Bang in astronomy and cosmology. And we use it to mean two different things, one of which we know a lot about, and one of which we don't know very much about at all. When we talk about the Big Bang Theory, that is a model for the history of the universe. We talked about it in the last video. We talked about the evidence from the redshift of all the distant galaxies. The distant galaxies are moving away from us. We talked about the fact that the cosmic microwave background radiation coming at us from all directions in space is evidence that at some point in the past, the universe was very small, very hot, very dense, and pretty much all the same temperature everywhere in the universe. That fact is the central supporting piece of evidence for the Big Bang Theory, which is the universe is now very big. All the galaxies are moving away from one another, which means in the past, as you go further and further and further back in time, the universe was smaller and smaller and smaller and smaller and smaller. So the history of the universe is one of expansion. That expansion might be uniform, it might be speeding up, it might be slowing down, it doesn't matter. Those are all versions of the Big Bang Theory that explains the observations we see of the redshift of distant galaxies and the cosmic microwave background coming at us from all directions. What the Big Bang Theory is not is a theory about the origin of the universe, how that expansion started, why that expansion started, and what happened before that expansion to quote unquote cause that expansion. What makes it confusing is we call that moment in time, that instant when the universe started expanding, we call it the Big Bang, right? The Big Bang refers to that instant that the universe began expanding. We know a lot about the 13.5 billion year history of the universe. We know what the universe was like a few million years after the Big Bang. We know what the universe was like a few 100,000 years after the Big Bang. Particle physicists can even tell us something about what the universe was like a few nanoseconds after that expansion started. Modern physics and cosmology cannot tell us anything about that moment of expansion, and certainly can't tell us anything about what might have caused that expansion. So the Big Bang event is not part of the Big Bang Theory. The Big Bang event is presumed to have preceded the Big Bang expansion, but it is something we know very, very little about. If you see a scientist telling you that we know how the Big Bang started or why the Big Bang started or what the Big Bang caused, they are not being straight with you. We have speculations, we have ideas, we have informed musings about what sort of thing could have caused the universe to begin expanding, but those are not part of any tested, verified scientific theory. So when we talk about the Big Bang, we are talking about a moment in time at the beginning of that expansion. The expansion is very well understood. That moment in time at the beginning is very poorly understood. And one of the reasons it's poorly understood is that it is a singularity. When we talked about black holes, we talked about the fact that if you get enough mass in a small enough space in the collapsing core of a star that's stopped fusing in its core and is trying to fuse iron into heavier elements and not making any energy, so gravity just squeezes that core away to nothing. What our theories predict is that core will get smaller and smaller and smaller, and we don't know of any force that can stop that collapse. So it tells us that the core shrinks away to zero size. Well, that doesn't really make any sense. Something with a mass of twice as massive as the sun, but zero size, doesn't really make sense. If you ask what's the density of that object, it's 2 suns worth of mass divided by 0 volume, which is infinity. It's not an answer. It's not a reasonable solution to that problem. It's not a reasonable mathematical statement that the density of a black hole is infinite. What we mean by a singularity, and we talked about this when we talked about black holes, is that it's a point where our equations of physics don't give us a reasonable answer. Well, what does the history of the universe look like if you go further and further back in time? The galaxies are right now expanding. The further back you go, the smaller and smaller and smaller the universe was, until there was a point in time where the whole mass of the universe was condensed into an infinitesimally small speck with zero volume. Well, of course, that doesn't make any sense. You can't have the whole universe of mass into zero volume. That singularity is a place where the equations of physics are telling us something unreasonable. They're giving us an answer of infinity when infinity is not a reasonable answer to the question of what is the mass or what is the density of the universe. Why do those infinities happen? They happen because the theory of general relativity says that gravity will pull that mass together smaller and smaller and smaller. And there's no limit to how small that object, that either the collapsing black hole or the universe as you get closer and closer to the Big Bang event, there's no limit on how small that thing can be. Because general relativity treats space and time and energy and mass as continuous. By continuous, I mean like the number line. You can have the number 1 and the number 2, the number 1.5 and the number 1.25, and 1.2 and 1.99999 and 1.9999999, and there's an infinite number of numbers between 1 and 2. Numbers are continuous. It turns out when we look at particles, though, particles are not continuous. You can't divide matter up infinitely. Eventually you get to particles that you can't divide anymore. Quarks and electrons and neutrinos. Likewise, when we talk about particle physics and the physics that governs fundamental interactions like the electromagnetic force and the strong force, the weak nuclear force, is they seem to be discrete. They seem to come in little energy chunks, and there's no smaller chunk than a certain amount. Think of the way money works, right? Within a particular country, say the United States, you can have $5 or $1 or 25 cents or 5 cents or a penny, but you can't have any amount of money less than a penny, right? You can't pay someone a third of a cent. Okay? You might be able to do it on Venmo or something. The gas stations can say the price is $3.49 and 9/10 of a cent, but you can't go into the cashier and give them 9/10 of a cent, right? Money is discrete. Energy in quantum mechanics is also discrete. Changes of energy, exchanges of energies, just like exchanges of money in the real world happen in integer numbers of cents. Exchanges of energy on the quantum number always happen in integer numbers of photons or gluons, the little packets of energy that transmit force between fundamental particles. This fact that general relativity treats everything as continuous, mass, space, and time, and quantum mechanics treats everything as discrete, particles and energy, means that those two theories don't always work well together when you apply them to the same problem. If I go back to my rack of textbooks behind me, I don't have my general relativity textbook because I loaned it to someone, but I do have this book on space-time physics. And I have this book on modern quantum mechanics. And the physics in this book treats space and time and matter and energy as continuous. And the physics in this book treats matter and exchanges of energy as discrete, as coming in little chunks like money does. And it turns out if you try to use these same, or these two books to talk about a single situation in the universe, they don't give you answers that make any sense because they're treating matter and energy in different ways. And that's not usually a problem because we usually don't need to use both of these things at the same time. We use general relativity when we're dealing with things that are giant and massive like stars and galaxies. We use quantum mechanics when we're dealing with little tiny things like electrons and neutrinos. There is nothing that is both giant and massive with a huge gravitational field that curves space-time and also teeny tiny like a quark or a neutrino, unless you take the whole universe and squish it down to the size of a quark or an electron or a neutrino. That's what is happening at the core of a black hole as it expands down into a singularity. Or if you trace the expansion of the universe back to the Big Bang event, the Big Bang instant, which would have zero volume, according to this book. This book says you can't really have zero volume. What's the solution to this problem? The solution to this problem, most physicists think, is we need a new physical theory that can do both of these jobs at once. We need what they call a unified theory. And when we talk about unification, we're talking unifying quantum field theories and general relativity. And a unified theory would be able to handle the situation of what happens if you take a star's worth of mass and put it inside of an atom's worth of size. What happens if you take the whole universe of mass and energy and squish it into the size of a proton? Right now, our physics isn't up to that task, and so the answer we get is infinity, singularity. It collapses away to zero, and nothing can stop that collapse. So we're stuck now, and we've been stuck here for about 40 years, where we kind of know we need a unified theory in order to answer some of these questions where singularities arise, but we don't have one, and nobody's been able to make one work. If you hear physicists talking about unified theories, or unification, or grand unified theories, or super unified theories, or string theory, or M theory, this is what they're talking about. They're talking about the recognition that we need physics to be able to handle situations where you apply both of these sets of tools to the same problem, and right now it doesn't work. So it's weird that we know physics is incomplete, but we don't know what the solution is. And until we solve that, the question of the Big Bang instant, when that expansion started, will always be probably unanswerable. Now, what can we do? We can get as close to that Big Bang instant as our laws of physics will allow us to. We can imagine the universe the size of a galaxy, the size of the solar system, the size of the sun, the size of the earth, the size of this ball, and ask, what would the universe have been like when it was that size? If I take every star and galaxy in the universe and squeeze it into this 3-inch aluminum ball, what would the temperature be? What would the density be? What kinds of particles would exist in that universe? We can answer that question surprisingly far back into history. We think we know what the universe was like, as I said a minute ago, a few thousand years after the Big Bang, a few minutes after the Big Bang, a few seconds, even a few nanoseconds after the Big Bang. So what we'll talk about in the next few videos is how close to that beginning of the universe can we get? And what tools do we have to use in order to get there? Telescopes are not going to do it for us, because telescopes can only see light that travels through space. And there was a time in the history of the universe where light could not travel through space. If you take everything in the universe and you squeeze it into a smaller and smaller and smaller sphere, eventually you reach a point where the universe is opaque. It's essentially a solid mass of matter, and light can't travel from one place to another. So there was no light going anywhere 1,000 years after the Big Bang. It would go from one atom and hit the next atom, and so there's no light bouncing around the universe from that time for us to see. In fact, what we're seeing when we see the cosmic microwave background is light from the time that the universe just got big enough to go from being opaque to transparent. That moment of what's called recombination, when electrons and protons combine into atoms, and hydrogen plasma turns into hydrogen gas, and those atoms get further and further apart. That's the time period of light that we're seeing when we see the cosmic microwave background radiation, that moment that the universe went from being opaque to being transparent, about 300,000 years after the Big Bang event. If we want to know anything about the time before recombination, before that time when the universe became transparent, we're not going to get it from traditional astronomy where we look at space with a telescope, because there was nothing to see 1,000 years after the Big Bang. There was no stars, there were no galaxies, there was no matter other than ionized hydrogen. It's so densely compacted that you couldn't see through it. So the tools for doing cosmology shift from the tools of astronomy to the tools of particle physics. What happens is we start asking particle physicists, all right, if you took all the matter and energy in the universe and you squeezed it down to the size of our solar system, how hot would it be? What would the energy of particles be? What would the density of particles be? How would particles behave at those energies and densities? And can we draw any conclusions about the way the early universe would have been from sort of modeling those interactions between subatomic particles in our particle accelerators. And we can know a surprising amount. It's impressive that we think we know what was going on in the universe 3 minutes after the Big Bang started, the Big Bang expansion. So in order to talk intelligently about some of this stuff, we're going to have to take a little detour in these past few weeks to talk about things like, well, particle physics. If the only thing in the universe a few minutes after the Big Bang was electrons and quarks and neutrinos, well, we have to know something about electrons and quarks and neutrinos because they were the main constituents of the universe. So that's what we'll need to understand in order to understand the beginning of the universe. The other thing we'll talk about, and we'll probably do this first actually, is the expansion of the universe as it goes forward in time, because there are different possibilities, right? Okay, the universe is expanding, has been expanding for 13.5 billion years. What next? Well, there are only a few possibilities. It could keep expanding forever, and the universe just goes on and on and on for an infinite amount of time. It could keep expanding and slow down and stop expanding at some point in the future. Or it could keep expanding, slow down, stop, and contract again. Just like a ball that you throw up in the air goes up and then back down, the universe could expand out and then gravity could pull it all back in again. So what we'll talk about at some point next week, maybe not the next lecture, maybe the lecture after that, is what we can say about the future expansion of the universe based on the expansion that we have seen so far. Can we predict something about how the universe will end up? So we've got two directions to go in before we reach the end of the semester. One, to talk about the future of the universe, which brings us into really interesting discoveries of the past couple decades, like dark matter and dark energy. And one, to talk about that initial first few minutes of the universe, what was going on there, and what can cosmology learn from particle physics, and what can particle physics learn from cosmology. It's really, really interesting the way these two sciences collide at the Big Bang, because cosmology is about the biggest things in the universe, and particle physics is about the smallest things in the universe, and it turns out we need to understand both to have any hope of understanding what that initial state of the universe was like. So that's where we're headed, and that's all I'm going to post today is this short little video. I'll have you read the chapters on the Big Bang as a review of the last video, and then starting next week we'll start talking about these two directions of the universe. How do we understand the future of the universe and the very, very distant past?